When we take a sample of data, we hope that our sample is reflective of the entire population. In that way, we can estimate what the population parameters are based on our sample. That's the essential question today, is how do we estimate population parameters? This really introduces the area of statistics that are known as inferential statistics. And just as its name infers, we're going to use sample data and statistics to estimate population parameters. And depending on the parameter we're estimating, we'll use another one. So if we were estimating means, as you would expect, x bar, the mean of the sample, estimates mu, the mean of the population. Similarly, if we are estimating standard deviations, which we're not going to do today, but the logic is the same, S, the sample standard deviation, estimates sigma, the population standard deviation. Another one which we're going to look at, very similar to means, is proportions. You see this a lot, especially with public opinion polls, where we'll estimate the proportion of people who support a ballot measure or a candidate by doing a sample, where P prime, also called P hat, will estimate a simple P. And here the P hat with the prime, the apostrophe on it, that's the proportion of the sample, and P alone, that's the proportion of the entire population. Now, granted, we're not going to be able to get a mean, a standard deviation, or a proportion that's exactly like the population. It should be pretty darn close, but probably not going to be exactly correct. And so instead of estimating, hey, the value is actually equal to this, what we're going to do is we're going to give a confidence interval. In other words, we're saying the statistic is probably got an extra syllable in there. Let's try that again. Probably close to the parameter. Some key words in there are probably and close. When we say probably, we're talking about an alpha level. We'll talk about that. And when we say close, we're talking about some error where we're off by a little bit. So let me dive into a little bit more about what I mean by alpha and what I mean by error. We're going to give a confidence interval. Just for this example, we're going to talk about means, but it works the same for standard deviations and proportions. We'll give the interval as a range as x bar minus some error, comma x bar plus some error. So if we can calculate the error that we might be off by, we can either subtract or add, and we get kind of a minimum or maximum possible value for the actual mean. We're saying the actual mean falls somewhere between our statistic minus the error and the statistic plus the error. Depending on our context, we'll calculate the error differently. There's 3 contexts we're going to look at today, and we'll look at the different formulas to calculate error. Alpha, the other half, alpha is our confidence level. How confident do we want to be to our actual solution? The more confident we are, the more lax we have to be with our error. Because if we want to be 99% confident, we're looking at a pretty large chance that there's an error that we have to move up and down. A large chance that there's an error between our statistic mean and our parameter mean. To be 99% confident that those are close together is a pretty big statement. 90% confident they're close together allows us to be a little more slack with the error. So, by the way, with confidence levels, we can technically use any percentage we want. Common percentages are 90%, 95%, and 99%. Sometimes I've even seen 98%. We're going to say those are common. No reason we have to stick with those, but generally in statistics, if we want to be really slack with our numbers, we use 90%. 95 is probably the winner. Most people use 95%. Generally, we say if we're 95% confident, that's pretty good evidence to make a conclusion. In some fields where an error would be disastrous, for example, the medical field. In the medical field, if you are wrong about your estimation, you could cost somebody their life. And so we want to be a little more certain, more confident. So we jump up to 99% in the medical field or other places where errors would be more severe. But really, there's no rule that you have to pick a specific confidence level. Visually, what this looks like is if we have a normal distribution with the mean in the middle. Actually, I shouldn't use, it should be x bar. We're saying the actual mean may fall above this value, x bar plus the error, or below the value, x bar minus the error. The actual mean is somewhere in here. We don't know where. The idea of our confidence level is that area in there is alpha. The total area of both sides together is alpha. We are 95% confident the true mean is somewhere in this range. We don't know where, but we're 95% confident the true mean is somewhere in there. So that's what we're talking about with a confidence interval. We want to find out what's the lowest possible and the highest possible value at this confidence level that the mean could be equal to. And then we interpret our results, the meaning of it. The meaning is we are 95% confident, and again that 95% might be 90%, might be 99, might be 98, might be 50% if you want to be really slack. That wouldn't be very good statistics though. We are whatever percent confident that the true mean, and I should highlight that also, depending on what we're estimating, it might be the true standard deviation or the true population. We are this percent confident that the true parameter is between some values, A and B. And we'll actually calculate those numbers. So that's the theory behind what we're doing. Let's actually do several examples here. And all the examples follow the same exact pattern. The only minor difference is the formula for the error. First, we're going to look at estimating a single mean with the population standard deviation known. If I know what the standard deviation is of the population, but I don't know what the mean is, this is how we're going to calculate the error. We're going to use z sub alpha over 2 times sigma divided by the square root of n. And you probably recognize sigma divided by the square root of the n. That's the standard error of the sample, which we saw in our previous chapter talking about the central limit theorem. Because we're talking about a sample. We took a sample, and we want to use the sample to estimate the population. This is a good formula to have handy for this chapter. And we use it whenever we know the standard deviation. So, for example, if exam scores are normally distributed with a standard deviation of 3 points, we take a random sample of 36 scores, which gives a mean of 68. Now, realistically, we know these 36 scores are probably going to be close to the actual mean of all the exam scores, but we don't know for sure what the actual mean is. So we're going to find out how close we actually are. First, we're going to find a 90% confidence interval for the true mean, for the population mean. Now, if we think about a normal curve, and we want to have 90% inside the middle, how much is going to be in each of these tails? Each of these tails, well, if there's 90% on the inside, 10% must be in the outside, and that has to be split evenly between the two tails. So we have 5% on the left and 5% on the right. So that's that whole idea of alpha over 2 that you see in the formula, z sub alpha over 2. Alpha over 2 says what's left divided by the two tails is 5%, or as a decimal, 0.05. So our formula for the error is z sub 0.05 times the standard deviation divided by the square root of the sample size. So to calculate our error, we need z sub 0.05. Let's go back to our tables to see if we can figure out what z sub 0.05 is. One way to do that is you can use the z table, but if you look at the second page of the tables I gave you, it says t distribution. We'll talk about that in a minute. But the very last row of the t-distribution down at the bottom of the t-table, some tables have infinity, some tables will even put a letter z. But what these are is these are the z-values that correspond with a tail at either 10%, 5%, 2.5%, 10%, or I'm sorry, 1%, or 0.5%. So for our data, we wanted the tail to have 0.05 in it. So if we go to our table, we want 0.05 in the table, and we go all the way to the bottom. That's the second column. We're going to use 1.645 for our z value. 1.645. 1.645 times the standard deviation, and we know the standard deviation of the population was 3 points, divided by the square root of n. N is the sample size of 36 scores. And so we've got 1.65 times 3 divided by the square root of 36, and we get an error of 0.825. This is the maximum possible error at 95% confidence for our mean. So the mean we found was 68. We're going to do 68 plus or minus the 0.825. So for the lower bound, we'll subtract 68 minus 0.825 is 67.175. For the upper bound, we'll do 68 plus 0.825, and we get 68.825. And so our interpretation, what we will say is we are 90% confident. In other words, 90% of confidence intervals constructed in this way will contain the actual mean. We are 90% confident the actual mean, or the population mean, is between 67.175 and 68.828. Oh, I'm sorry, that should be a 5, not an 8. I can't do calculators. There we go. This is inferential statistics, using our sample to make an inference or an estimate of the population. We're 90% confident the actual mean is between these values. Now what happens if we adjust the confidence level? What if we did the same problem, but instead of a 90% confidence interval, we were asked to find a 95% confidence interval? So now we're looking at the same situation, but this time our area in the middle we want to be 0.95. Not 90%, but we want more area. More area, 95%, moves us out. So what's that going to do to the air? It's going to move the air out. There's 5% left over for the two tails. 5% divided by 2 is 0.025 in each tail. So our error is going to be z sub 0.025 this time. 0.025 is how much is in each tail times the standard deviation divided by the square root of n. So if we go back to our table, This time we want 0.025 in the mean, in the tail. So 0.025 in the tail, that's the center column. Now z is 1.96. So the error is equal to 1.96 times the standard deviation of 3 divided by the square root of n, which is 36. 1.96 times 3 divided by the square root of 36. Now the error is bigger. Now the error is 0.98. So now we take the mean, which was 68, and we say plus or minus the error of 0.98. If we subtract 0.98, we get 67.02. If we add 98, we get 68.98. This is our confidence interval to be 95% confident. We want to be a little more confident, so we need a little bit bigger of a range to say, yeah, we're even more confident now, the true mean. We are 95% confident. The population mean is between 67.02 and 68.98. So notice as the confidence interval gets bigger, we need to cover more area, which means we need a bigger error, a bigger confidence interval to match a bigger percentage. How does the sample size affect things? What if instead the sample size was 100? Now find a 90%, going back to comparing it to a confidence interval. I'll use CI for confidence interval. So we've seen this situation before, the 90% confidence interval means we've got 0.9 in the middle, 0.10 for the outside, which means 0.5 on each, dividing that by 2. So the error is z 0.05 times the standard deviation divided by the square root of n. So we want a z with 0.05 in each tail. We saw that before. 0.05 is the second column. 0.05 in each tail is 1.645. So the error is 1.645. Make sure I got it right. 645 times the standard deviation, which is 3, divided by the square root of the sample size. Now the sample size this time we're saying is 100. Notice a bigger sample size, we're dividing by a bigger number. So now the error is 0.4935. How did that compare to the error in A? It was 0.82. Now the error is much smaller, 0.49. So now we say our mean was 68, plus or minus the error of 0.4935. So if we subtract it, 68 minus 0.4935, we get 67.51. We can round it. 68 plus 0.4935 is 68.49. So we are 90% confident the population mean is between 67.51, and 68.49. Notice as the sample size got bigger, the error got smaller. And that makes sense because the more people you interview, the closer that should be to actually interviewing everybody. Because the closer to everybody you get, the closer to the true value you get. Now sometimes you kind of want to go the opposite way as you set up a research study. Sometimes you want to know before you get started, how many people do I have to interview? How many people do I have to ask this question in order to get a good data value, a good confidence interval? The way we find the desired sample size or the required sample size for a mean where the population standard deviation is known is we use the formula. Actually, this is solving the error formula for n. Solve the error formula for n, you get n equals z squared sigma squared divided by the error squared. So, for example, if the standard deviation for the age of college students is 15, and we want to be 95% confident the sample mean is within 2 years of the actual mean. If I can spell. How large of a sample is needed? Well, again, we want to be 95%, 0.95% on the inside, which means we have 0.05 for each tail. Divide by 2 is 0.025. So n is z sub 0.025 squared sigma squared divided by the error squared. Going back to our table, we want z of 0.025. Let's see, 0.025 in the tail, that's the middle column, 1.96. So z is 1.96 squared times sigma, standard deviation of the college students, is 15 squared, divided by the error. We want to be within 2 years, so 2 is the error squared. So on our calculator, 1.96 squared times 15 squared divided by 2 squared, we get 216.09. Now we want to be careful with rounding, though, because 216, yes, it rounds down to 216, but that's not enough people to get the actual confidence we want. So we need to go up and say we need to interview 217 to be within 2 years of the actual mean. So that is a single mean when we know the population standard deviation. But how realistic is that? How often do we know the standard deviation of everybody without knowing the mean of everybody? That's actually not a very realistic situation at all. Instead, usually we're estimating a single mean with the population standard deviation unknown. If we don't know the standard deviation, we're going to kind of have to fudge on it. And the way we fudge is we are going to use what is called the student t distribution. Often it's written as t with, we'll say, n minus 1 degrees of freedom. We have these degrees of freedom with the student t distribution. The student t distribution is actually very similar to the normal distribution, but with more area in the tails. The more area in the tails makes up for not knowing the actual standard deviation. It turns out, though, that as n is greater than 30, it is very, 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 very similar to the normal distribution. In fact, this is one place where the book and I disagree in interpreting our statistics. If n is greater than 30, I prefer to use the normal distribution because it's actually just as accurate. The book and I disagree, and I'm not going to fight this one because it's not a big deal. You get the same answer both ways. So I'm going to say we'll still use we'll still use the t-table in all cases when we don't know the standard deviation. Okay. With that said, the error is calculated much the same way. We're just going to use the t-table of alpha over 2 times, we'll use s, the sample standard deviation, divided by the square root of n. So let's do an example. Let's say we had 15 acupuncture subjects who recorded the following sensory rates. Let's see, our data is 8.6, 9.4, 7.9, 6.8, 8.3, 7.3, 9.2, 9.6, 8.7, 11.4, 10.3, 5.4, 8.1, 5.5, and 6.9. We are going to construct a 95% confidence interval for the true mean. Notice in this example we don't know anything about the population. All we know is the sample, and this is much more realistic. Our sample, we know the number of values in the sample. There's 15. We have to know the degrees of freedom. The degrees of freedom for almost everything we see is always one less than the number of data values. So there's 15 data values. The degrees of freedom is 14. In class, if you want to ask why degrees of freedom is one less, we can talk about it in class, but I'm not going to get into it in the video, but feel free to ask in class. for now. Degrees of freedom, just one less than the number of data values. We need to know what our estimates are for the mean and the standard deviation, x bar and s. To help us with that, we're going to use our calculators. On our calculator, we're going to program our data in. Remember, we get that by clicking the Stat button and Enter on Edit. If there's already data in there, you can scroll up to L1 and hit Clear, Enter. And we'll type in our data points. 8.6, Enter. 9.4, Enter. 7.9, Enter. 6.8, Enter. 8.3, Enter. 7.3, Enter. 9.2, Enter. 9.6, Enter. And I'm off my screen, so we'll move my calculator over. After 9.6 was 8.7, Enter. 11.4, Enter. 10.3, Enter. And now I'm on the next line, so we'll move the calculator over. 5.4, Enter. 8.1, Enter. 5.5, Enter. 6.9, Enter. And now we'll hit second, quit. Stat again and go over to calculate the one variable stats. On the TI-83, you just have to type in second L1, which is above the number 1. The TI-84 gives us a prompt, which is nice. We just have to hit calculate. And it gives us all sorts of information. We need to be able to pull off the important information. We need to know the mean, which is 8.23. And we need to know the standard deviation. And remember, because this is a sample, we need to use SX, 1.67. 1.67 is the standard deviation. So again, very similar to what we did before. We want to calculate a 95% confidence interval. We want 95%, 0.95 in the middle, which means 5% for the outside, divided by 2 is 0.025. 0.025 for each. So the error is t sub 0.025, that's the amount we want in the tail, times the standard deviation of the sample, divided by the square root of n. So go back to our tables. And I'm going to clear out some of this stuff. In the past we were using the infinity because it's going to be really close at infinity to the normal, but actually the rest of the table is our t values. Notice the first column is df, our degrees of freedom. We said there were 14 degrees of freedom. We also said we wanted 0.025 in each tail. So 14 degrees of freedom with 0.025 in each tail. T is 2.145. 2.145 times S. S, the standard deviation that we found was 1.67, divided by the square root of 15. So on our calculator, 2.145 times 1.67 divided by the square root of 15, we end up with 0.925. So we'll take our mean, 8.23, plus or minus the error of 0.925 to get our confidence interval. First, subtracting 8.23 minus 0.925 is 7.305. And 8.23 plus 0.925 is 9.155. This was a 95% confidence interval, so we are 95% confident. The true mean is between 7.305 and 9.155. That is our confidence interval. The only difference here was that we had to use a t-value based on the degrees of freedom. So we're just using a different chart to find out what the new t-value was. Much more realistic, though, because most often we do not know the population standard deviation. One more type of confidence interval I want to look at, though, is proportions. A proportion, we'll use p hat or p prime, some people say. The way we calculate a proportion is we take some x divided by n, or the number of successes divided by the number of trials. Notice this sounds like, and it actually is, a binomial distribution. But instead of saying the number of successes out of the number of trials, we express it as a proportion. 0.83 of the people are right-handed. It's a proportion, expressed usually as a decimal. And it turns out that these proportions are actually p hat or p prime is normally distributed with a mean of p, a mean of the actual proportion, and a standard deviation, which is the square root of pq divided by n, where q is equal to 1 minus p. In other words, q is the proportion that don't do what we want, the other group, if you will. And just like before, everything's going to be the same as the other two examples. The only difference is the error formula is slightly different. We'll still have z sub alpha over 2. Proportions will still use a z. But we'll multiply by the square root of pq divided by n. And we'll actually be p hat and q hat because we're going to have to use our sample proportion and our sample other proportion. So let's do an example. Let's say 500 randomly sampled adults were asked if they had a cell phone. $421 responded yes. Find a 99% confidence interval for the true proportion. Couple things we need to know up front. What is the proportion of our sample, p hat? 421 responded yes out of 500. As a decimal, that's 0.842. So q hat, that's the other group. Those that did not respond yes, those that said no, that's 1 minus 0.842. The other group is 0.158. Okay. Now again, we want to make a confidence interval so that the true proportion is somewhere in the middle at 99% confidence. which means we have 1%, 0.01 for the tails. Split up evenly, that's 0.005 for each tail. So our error is z sub 0.005 times the square root of p hat q hat divided by n. Let's go to our table. Let me erase off the other problem here. We want 0.005 in each tail. That's the last column. And the z's are the same as infinity. So our t value we're going to use, or our z value we're going to use, sorry, is 2.576. 2.576. So the error is 2.576 times the square root of p hat, which is 0.842, times q hat, which is 0.158, divided by n. We sampled 500 people. So on our calculator, 2.576 times the square root of 0.842 times 0.158 divided by 500 is 0.042 approximately. So the actual proportion is going to be 0.842, our sample proportion, plus or minus the error of 0.042. So grabbing our calculator, 0.842 minus the error of 0.042 gives us 0.8. 0.842 plus 0.042 is 0.884. And now we have a 99% confidence interval. We are 99% confident the true proportion, or the population proportion, is between 0.8 and 0.884. The true proportion of adults with cell phones is between 80% and 88%. We're 99% confident of that based on our sample. One last thing that I want to look at with this proportion. Again, I want to hit on required sample size. Required sample size, again, we take our error formula and we solve for n. So we end up with n is equal to z squared p hat q hat divided by the error squared. So if we want our proportion to be within a certain percentage, we would use this formula to find out how many people we have to interview. So if a company, let's actually move this up, a company wants to know how many cell phone users over 55 years old, if I can spell years, I got an extra letter in there, use texting. How many must be interviewed to be 90% confident the true proportion is within 3 percentage points. You see this a lot of the times in political campaigns. We are within 5 percentage points, plus or minus 5 percentage points. They have figured out how many people they have to interview so that their results are going to be within plus or minus a certain percentage, using this formula. Now here's an interesting fact. We don't know what p hat and q hat equal. Because we haven't done the study yet. We want to know how many people we have to interview to get the results we want. Well, in this case, we're going to make them as equal as possible so that their product will be as large as possible, kind of giving us a worst case scenario. So if it's a 50-50 chance, 0.5 and 0.5, that'll give us the largest product of PQ. The error we know we're looking for is 3 percentage points, or 0.03. Our Z, we want to be 90% confident. So we want 90% on the inside. 5% then must be on each side, 0.05. So Z 0.05 is equal to, off of our table, 5% in each tail is the second column, 1645. 1.645. Let's go to the formula. N equals Z, 1.645 squared, times P hat, which is 0.5, times Q hat, which is 0.5, divided by the error, which is 0.03, squared. Let's type that in our calculator. 1.645 squared times 0.5 times 0.5 divided by 0.03 squared. We get 751.67, which means 751 won't quite be enough to guarantee a 3 percentage point error. So we are going to interview 752 people in order to be 90% confident the true proportion is within 3 percentage points. So we talked about 3 different cases. What I want to notice is that each case is exactly the same. Probably labeled this wrong over here, actually. Alpha is the amount in the tail, back in example 3 of part B. Alpha is the amount in the tail. What we'll do is we will take our estimate and add or subtract the error based on the confidence level and the error formula for the situation we're talking about. Proportions use one formula. If we know the mean, if we know the standard deviation, or we don't know the standard deviation, we use another formula. Start taking a look at them on the homework. We'll talk about them more in class, and this is really going to be the most exciting part of statistics, where we get into doing real inferential statistics from here on to the end of this course. We'll see you in class.